let's see, what's a good reaction? N2 plus O2 goes to 2 NO. If I don't want to do any work during this reaction, what do I need to make sure happens?
Constant volume.
Constant volume. Delta V equals 0. No work, because W equals P delta V, right? And so 0 at delta V equals 0. And so when delta V is 0, or I don't do any work, delta E equals delta H at delta V equals 0. So you sort of have to know the little derivation. How do you get this term to 0? How do you get the system not to do any work? So what type of calorimeter do we use if we want delta V to be 0? Bomb calorimeter. Why is delta V 0 in a bomb calorimeter?
It's a rigid body.
It's a rigid body. The volume doesn't change when we do the calorimeter, right? When you perform calorimetry in a styrofoam cup, the volume's allowed to change. So this is the condition when delta E equals delta H. You'll hear this again in like a year or two when you take advanced thermo, and so hopefully you'll remember it. Because all of this stuff is what advanced thermo is about, how these equations are related. Yeah. But getting a good start on it now will help you. Yes?
I understand you mentioned mechanical work, so I guess just to add on to that question, I know you mentioned chemical potential work, like chemical potential, like I guess right when you initially brought up work. Is that something that we have to?
Chemical potential.
Right, like mu. I remember you wrote.
Let me take a look. Was it in the notes or was it on the board? Or,
You might have wrote it on the board. But
let's take a look. Have we talked much about chemical potential? No. So I don't think it's going to be on the exam, but let's take a look in the notes. Come on, you can do it. Maybe potential energy? Now, I mean, mu is the symbol for chemical potential, but to be honest, I don't remember where we went through it. If you find it in the notes and can show me and refresh my memory. I don't see it. Does anyone see chemical potential in their notes? Well, getting there. There we go. No. Stuff will rot your brain. Okay. So when we're talking about work, we had what lecture was working? 7? So here's the different kinds of work right here. Different kinds of work, mechanical, electrical. Oh, this thing right here. We didn't talk hardly about that at all, if not at all. So the most important part of this work slide, so this is lecture 7, slide 9 for those of you listening at home. The most important part of work is P delta V. And it's good just to remember that you can have other kinds of work. Electrical, surface tension, we didn't talk about that at all. So, you know, you can write these equations, they're in a box, right? So you can write them down on your sheet, but I guarantee you, you might just be interested in this one, not the others. Yeah, so just know that there's different kinds of work. So whether, you know, electricity is a source of work, mechanical or change in volume is a source of work, and they're equivalent, right? That's the most important part. Yeah?
You didn't talk any about the work for electric.
Not really. I mean, we have the refrigerator problem, right? So that's kind of it. I'm not gonna say we have 6 moles of electrons. You know, you guys kind of know what Faraday's constant is. You kind of know what potential is, but don't worry about it too much. Just know that you've got different kinds of work. That's the most important.
What about surface tension?
We didn't talk much about it, right? Probably not going to be on there. Okay, other questions? Yeah?
Why was that?
Oh.
No, that's fine. It just said delta E equals Q minus W. On the board, I thought you had a plus W.
Oh, sorry. That's my bad. That's a typo.
So it should be plus.
Q plus W. Yeah. Q plus W for sure. So let's just review that. So what am I talking about when I say Q plus W? What, or delta E? The delta E of what? Yeah, that's a good answer. So this is delta E of the system is Q, W. Are my signs right? Plus, plus, right? Which one's for an exothermic reaction? Q going out. This one's for an endothermic reaction then. And so this describes the internal energy change of my system. So if I'm putting Q into my system or I'm putting work into my system, delta E is going up, right? If I'm taking heat out of my system or taking work out of my system, you have a negative sign here. So my internal energy is going down. And so this equation works with this diagram when you think about the delta E of the system. So if you're taking heat out, internal energy is going down. If you're putting heat in, internal energy is going up. So this will help you with confusion on signs and stuff like that. You got away with it on the last homework. I apologize for that. Go ahead.
Endothermic process is Q plus, right? Is that what you just said?
Yes, endothermic is Q plus.
Okay.
Endothermic. You have to put heat in to make it go. Endothermic, it absorbs heat, so Q is plus. Exothermic, which is somehow the easy one to remember, gives off heat. So this can help you solve all these problems. And we talked a lot about this diagram in the context of entropy, right? But it also can help you solve internal energy problems. It's good, no? Other questions? Yeah.
Well, we have a question on the test where it's like, 0.5 moles of acetic acid, and it's K, SP is something, and what's the pH of 1 liter of water?
Did you have one of those on your homework?
No. So no.
What?
Or maybe
You had one about pyridine, right?
we have here.
What's the difference between that and acetic acid?
One's a base, one's an acid.
Well, yeah, but nothing. So acetic acid, what's the formula? Right? Acetic acid. What does its dissociation look like? I assume you want to put this in liquid water. Is acetic acid liquid, solid, gas? Does anyone know?
Gas.
It's liquid. High van der Waals forces from this carboxylic acid group makes it a liquid. Okay, so what's going to happen when we put acetic acid in liquid? Water.
The last H was associated.
Yeah. Minus. Is this equation balanced?
Okay.
Yeah, it's good, right? Water, water, acetic acid, I got it. Why did I write this H3O plus?
It's not associated with associates.
Yeah, the proton is always kind of stuck with a water molecule. So I could have written this as a proton. That's cool. But I've got water on this side, right? So I just put the water in on both sides. So what's the reaction quotient for this thing? I can write out the whole thing if I want, right? How do I simplify the reaction quotient?